Here we're going to talk about the Chatelier's principle. So this is all to do with this idea of an equilibrium, okay? So let's read through and then let's develop our understanding. So the relative amounts of all the reactants and the products at equilibrium depend on the conditions. So whenever you've got a reaction, the amount of reactants you've got and the amount of products you've got depend on the conditions. If there's an equilibrium present. So if a system is at equilibrium, when you make a change to the conditions, the system responds to try and counteract the change. So one thing we need to be really clear on is what equilibrium actually means. So equilibrium, what it's not, well, it's not the reaction has stopped. Okay? So equilibrium does not mean the reaction has stopped. However, if you have got reactants that turn into products, well, in an equilibrium, it's reversible. So reactants turn into products, but products can also turn into reactants. Okay, so they can turn back the other way. Now, equilibrium is when the forward reaction rate, so this is reactants turn into products, is equal to the backwards reaction rate. So where the products turn back into reactants. So if reactants turn to products the same rate as products turn back to reactants, well, the concentration or the relative amounts of the reactants and products won't be changing. So if the forward reaction rate equals the backward reaction rate, the concentration of reactants and the concentration of products will be unchanged. Just to repeat, this doesn't mean the reaction stopped. It means the reactants turn into products exactly the same rate as products turn into reactants. Finally, the symbol we often use for a reversible reaction is this symbol like this. Okay, so here's a question we're going to look at together, and we'll read it through. The equation shows one stage of the manufacture of sulfuric acid from sulfur dioxide. So I've got my sulfur dioxide and my sulfur dioxide and my sulfur trioxide, and this is a reversible reaction. The reaction is exothermic in the forward direction. Okay, so that means in that direction it's exothermic. Exothermic means it releases heat, so more heat's given off here. If it's exothermic in the forward direction, well then it's endothermic in the backwards direction. Okay, so that means more heat is taken in. Now, it says use Le Chatelier's principle to predict the effect of increase in the temperature on the amount of sulfur trioxide produced at equilibrium. Give reasons for your answer. So, going back to the first page, it says when we make a change, the system tries to counteract the change. So, if we increase temperature, the system tries to counteract it. Therefore, if we increase the temperature, the system will try to reduce the temperature. Okay? So, the question says we're increasing the temperature. Okay? So the system will try and reduce the temperature. And the way we're going to reduce the temperature is if we do the endothermic reaction, because endothermic takes in heat. So the backwards reaction is endothermic, therefore will take in heat. Therefore, the position of equilibrium moves left to make it do more of the endothermic reaction. And if the position of the equilibrium moves left, it means you will produce less of the product sulfur trioxide. Okay, so let's just read through this. So, because the forward reaction is exothermic, if you increase the temperature, well, the system always tries to counteract it and reduce the temperature. So the backwards reaction is endothermic, so it takes heat in. So if you want to increase the temperature, well, the equilibrium will move left to produce more of the reactants, and therefore it will make less of the product. So by increasing the temperature, you will make less of the product. So it says predict the effect. Well, I've said the effect. We're going to produce less product. And the reason is because the forward reaction is exothermic, so the position of the equilibrium moves left, and we're trying to reduce the temperature from it. Now, this one isn't about changing the effect of the temperature, so let's read what the question is here. I've got the same reaction, it's reversible, sulfur dioxide into sulfur trioxide. My reactants here, and my products here. But this time we're predicting the effect of increasing the pressure on the amount of sulfur trioxide produced. So if I increase the pressure, what happens to the amount of my product? Well, if I increase the pressure, again, the system tries to reduce it. System tries to counteract it. So if it tries to counteract it, the system will try to reduce the pressure. So when we look at pressure, we're talking about how many molecules are there, so we need to count. So on the reactant side, I've got 2 sulfur dioxide, so I've got 2 molecules of those, and 1 oxygen, so that makes 3 molecules on the left. On this side, I've only got 2 sulfur trioxides. So on the left-hand side, I have 3 molecules, and on the right-hand side, you've got 2 molecules. So if you increase the pressure, well, it's going to feel a lot worse on the left-hand side because you've got more molecules there. So, because there's more molecules on the left-hand side, the equilibrium will shift right to reduce pressure. If the equilibrium shifts right, it will produce more product, and the product is sulfur trioxide. Let's check it through. Predict the effect of increasing the pressure. Well, I've said the effect will be it will produce more product, and the reason is because there are more molecules on the left-hand side than on the right, pretty much. I've got 3 on the left and only 2 on the right.